In this video, we will be covering the squeeze theorem. It's also known as the squeeze principle or the sandwich theorem, so perhaps your calculus teacher called it one of those things. And this is a very, very powerful theorem. And basically what it says is that if two functions, in this case say f of x and h of x, approach the same limit as x tends to a, then any function that's between these two functions near x equals a approaches that same limit. And you can see here that near x equals a, g of x is greater than or equal to f of x, but it's less than or equal to h of x. And as x approaches a, both f of x and h of x approach this limit L. So g of x, this theorem says g of x must approach L as well. From this graph you can tell that g of x approaches L, but usually you're given an algebraic limit to evaluate, and the function g of x is not easily graphable. But this theorem in essence says that if f of x is less than or equal to g of x is less than or equal to h of x near x equals a, and this is some arbitrary region around x equals a, near x equals a, but not necessarily at x equals a, and if the limit as x tends to a of f of x equals the limit as x tends to a of h of x, then the limit as x tends to a of g of x, if both of these equal L, then the limit as x tends to a of g of x also equals L. The statement written here is for two-sided limits, but hopefully you can see from the graph here that intuitively you can expect the same thing for one-sided limits. So say you're coming in from the left, you're approaching x equals a from the left, and f of x is less than or equal to g of x, which is in turn less than or equal to h of x in some region to the left of x equals a. So for values of x less than a, close to a. Then, and also if the limit as x tends to a of this bottom function f of x is equal to the limit as x tends to a of this top function h of x, both coming in from the left, then the limit as x tends to a coming in from the left of g of x also equals that limit. In this case it's L. So let's say if we're looking at, say, for left-handed limits. And the same thing applies for right-handed limits, so I'm just going to write it for left-handed limits. If f of x is less than or equal to g of x, which is less than or equal to h of x, for some x less than a near x equals a, but not necessarily at x equals a, and if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right, or from the, sorry, if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the left of h of x equals L. If both of these limits are L, then the limit as x approaches a from the left of g of x also equals L. And this is a statement about left-handed limits, and it's also true coming in from the right. You know, if you had said if f of x is less than or equal to g of x is less than or equal to h of x for some x greater than a, near x equal to a, but not necessarily at x equal a, and if the limit as x approaches a from the right of f of x equals the limit as x approaches a from the right of h of x, and say these are both L, then you can say that the limit as x approaches a from the right of g of x is L as well. So what I've written is for left-handed limits here, but it applies to right-handed limits as well. And here is a statement about the two-sided limits. Now, coming back to the graph, I'm going to have to mention something that's pretty important for you guys to realize, and that's you'll notice that h of x is greater than or equal to g of x, which is in turn greater than or equal to f of x near x equals a, but I've drawn an open circle at x equals a. And this is just to say that this ordering need not apply at x equals a. For example, f of a might be here, g of a might be here, and h of a might be here, might be between the two. So this isn't the order that they're in near x equals a, but this squeeze theorem still applies. So even if at x equals a, g of x does not lie between h of x and f of x, or I should say g of a does not lie between h of a and f of a, as long as near x equals a, g of x lies between f of x and h of x, and these functions have the same, h of x and f of x have the same limit as x approaches a, then you can say that g of x has that same limit as well. And actually the functions here don't even have to be defined at x equals a. So f of x, g of x, or h of x, or perhaps all of them, could potentially be undefined at x equals a, but as long as near x equals a, f of x is less than or equal to g of x, which is in turn less than or equal to h of x, and that's another way of saying g of x is between f of x and h of x. And if these two outer functions, f of x and h of x, have the same limit as x tends to a, then you can say g of x has that same limit as well. I mentioned at the beginning that this principle or theorem is very powerful, and I'm going to have to show you an example so that you can see why. So let's say we want to find the limit as x approaches 0 x to the fourth times the sine of 3x squared over x to the eighth. So looking at this, you have really no idea about how this graph looks or anything like that. This looks to be a fairly complicated function, and if we tried plugging in 0 here in this sign, we get sine of 0 over 0, which is an indeterminate form, and not really sure what to do after that point. But what I want you to consider is this piece of this function right here, just this sine 3x squared over x to the eighth. And you hopefully realize that no matter what values you input for x, because you're taking sine of this quantity here, sine always, no matter what, ranges between +1 and -1. So let's see what happens here if we were to multiply each term by x to the fourth. And remember, when you multiply all portions of an inequality by a particular number, you're going to have to consider whether that number is positive or negative. And x to the fourth, when you're approaching when you're approaching 0 from the right, a positive number to the fourth is going to be a positive number. But when you're approaching from the left, a positive number to the fourth is still going to be a positive number. So you can keep the inequality, the direction of the inequalities, the way it is now. So you have x to the fourth times sine of 3x squared over x to the eighth is less than or equal to x to the fourth, and this is greater than or equal to negative x to the fourth. Now let's consider the limits of these two outer functions here. So the limit as x tends to 0 of negative x to the fourth, well, as x gets close to 0 coming in from the left, you're going to be dealing with a very small negative fraction. A negative fraction to the fourth is going to be an even smaller negative fraction. You negate that, you'll get a negative but very small fraction. Coming in from the right, you're going to get, you raise a small positive fraction to the fourth. Or sorry, coming in from the left, you're going to raise a small negative fraction to the fourth. You're going to get an even smaller but positive fraction. You negate that, you'll get a really small negative fraction. Coming in from the right, when you raise a small positive fraction to the fourth, you will still get a very small, even smaller, but positive fraction. You negate that, you will get a very small negative fraction. And as the fraction you're raising to the fourth, whether positive or negative, gets closer and closer to 0, then that fraction raised to the fourth gets even closer to 0. Negating it, that just changes the sign of it, but it's still a number very, very close to 0. So as x approaches 0, this limit is equal to 0. And by the same reasoning, considering this function on the right, the limit as x tends to 0 of positive x to the fourth, remember, you're doing the same thing here, you're just not negating after raising the small fraction to the fourth power. And I'm saying small fraction because we're considering quantities very, very close to x equal to 0. So the limit as x tends to 0, x to the fourth goes to 0 as well. So these two outer functions go to 0. And looking at this graph here, this negative x to the fourth was our f of x. The positive x to the fourth is our h of x. Our a here is 0. And the g of x is this function we have in the middle, sine of 3x squared over x to the 8th. And we saw that these outer functions here go to 0 as x tends to 0. So negative x to the fourth and positive x to the fourth go to 0 as x goes to 0. So this means that the function in the middle also goes to 0 as x tends to 0. Thus, the limit as x tends to 0 of x to the fourth sine of 3x squared divided by x to the 8th equals 0 by the squeeze theorem. I'll just abbreviate theorem with THM.